So hello everyone, my name is Balázs Keszthelyi from vNova Limited. First of all, I'm very happy that after skipping the last 5 years, I again have the opportunity to present at GPU Days, and I'm especially humbled that I can do it at my former university. I also like to thank for my colleague Michele Sana, who isn't here in person, but who was putting a lot of effort into this work on the coding side. vNova is a London-based company, primarily focusing on novel compression algorithms. What you need to know about the compression market and in general video and image compression algorithms is that basically developing them is an uphill battle, because even for very minuscule perceptual gains, there is always a very disproportionate computational cost that you need to put in by making the algorithm more and more complex. The vision of the founders of vNova was to try to, if not to break the cycle, but to position the company to be more competitive in this sector by changing the inherently serial nature of other compression techniques and develop the world's first inherently massively parallel video coding algorithm, which is now known as Perseus. This is what leads us to the other claim, that this is AI-based. So obviously once it was massively parallel and it was already running on GPUs, we just happened to be lucky essentially to be in a space where ample amount of compute capacity was available us to also become the first company who managed to deploy in production codec that is using deep learning in its very core on the transform level. So basically these are the two notable and pioneering things that Perseus is famous for. How many of you was watching the series Silicon Valley? Okay, only one. So basically, in short, what that series is about is that it's about a startup called Pied Piper, whose founder is coming up with a fantastic compression algorithm that is beating absolutely everything else. It's very, very imaginary and pioneering. But then he struggles to figure out how to make it into a product. So despite he's the founder, he recruits a professional CEO to figure out how to sell it. And ultimately, what the irony is in the series is that he comes up with possibly most unimaginable, least pioneering thing, a gray metal box, which is like enterprise-grade solution. And this is how fantastic pioneering ideas can turn into business-like and somewhat boring applications. Why is this interesting? Because this is precisely what we do as well. So our box is called peeling. And basically, the major reason why we are doing this because it makes sense economically. Because one of our so actually the first target market is the broadcast industry. And what you need to know about the broadcast industry is that it's a particularly conservative space, meaning they love boxes. So their idea of integrating a new technology is not like changes in a non-existing complicated software pipeline. Their idea about integrating anything is fitting a box, like a physical box, into a prescribed space, which is having some standard size. Now, these kind of boxes are having certain properties that are tried to capture here. But essentially, the long story short is that boxes are usually made of hardware in a sense that even the components are usually ASICs, but if not ASICs, then they are FPGAs. All the similar boxes that were developed before, as a result, are having certain kind of characteristics. For example, they are redundant in a sense that if they are capable of dealing with multiple video streams at the same time. That is usually done by separate pieces of hardware, which means that enabling or disabling one of those additional video streams is having absolutely no impact on the already running parts of the system, because there isn't anything shared between them. So higher density is actually achieved with multiplication of the available resources. Now, tiny little problem that we had is that we are not targeting ASIC or FPGA solutions, at least not yet. So the challenge here, what this presentation is about, is that how to try to force the GPU to behave a bit more like these systems, to mimic some of their generally good behaviors. So what we can tell about the problem is that we are talking about a number of video streams to be processed by a limited and fixed hardware design. The configurations are flexible, some may be higher resolution, but then we have a fewer number of streams to process, etc., etc. The incoming frames are coming in roughly with a certain timing of the inverse of the frame rate, but their ordering is not actually guaranteed. So there may be some slight fluctuation in that regard. On the other hand, the output is expected to be in a very similar fashion. So effectively, one needs to be able to tell a precise upper bound of latency of the processing. So effectively, it means that some kind of quality of service is expected. And also, as a last thing, so as an implementation of redundancy, it is important that if there is any kind of error, it ideally should only affect one of the video streams and not necessarily bringing down the whole system. So this is a fairly normal embedded systems problem, to be honest. And it is not impossible to have software solutions having these properties, but these problems normally in embedded programming space are handled A, on CPUs, B, by having very rigid assignments of tasks, effectively having prescribed recipes of this task is running now, then the other is taking over, and these are already fixed at every time they happen to run on the very same core, and so on and so forth. So so with setting thread affinity and synchronization properly, normally with CPU programming, similar behaviors are achievable. Now, in general, for these kind of problems, it would be the normal course of action would be to come up with a multi-process design, because multi-process is supposedly offering the benefit of process isolation, which would enable us to only allow only one process to fail instead of the whole system. One tiny little problem is that process isolation is non-existent on GPUs, so you can very happily lock up the entire GPU from only one process. So as good as such a design would sound, in practice it doesn't necessarily mean any benefit. But it's important that these kind of systems are doing a lot more than just compression. So for the rest of the system, process isolation is still beneficial. So as a result, that is the baseline of the design. And then multi-threading may be considered if we want to do something more intelligent with regards to GPU synchronization. Okay. What can go wrong with multiprocess? So let's just do that. So for example, this can go wrong with multiprocess. So as I try to color code this effectively, it will have some relevance later, but the blue ones are input operations, so basically uploading data to the GPU. The green ones are some kind of compute. and the red ones are the output operations when you download whatever was produced on the GPU. So this is something that with some particular hard version of a vendor that I won't name now could actually happen. The most interesting behavior is, for example, when a unit length PCI Express upload could become somehow sliced. Actually, in reality, it was worse. It was trying to force some kind of quality of service, so achieving suboptimal upload throughput for all the processes in the end. So basically, what is wrong with this? So one obvious problem is that you can see lots of gaps. So it's probably an indication that the hardware is not necessarily utilized efficiently. The other problem is like, can you tell the latency of the system from this? I mean, pretty much anything can happen. Still, even in this scenario, some very, very high upper bound of latency exists. So mathematically, you could argue that, okay, there is a guaranteed latency even if you don't do anything, but such a high latency is absolutely impractical for the system. Okay, what's the problem here quickly? So that the streams are absolutely not knowing about each other. Okay, why is that? Because in OpenCL, if you are familiar with it, all the sharing and synchronization capabilities are depending on the assumption that everything is within one OpenCL context. And although there is guarantee for thread safety in OpenCL, but in general, one context belongs to one process specifically. So necessarily, due to implementation reasons, all of these video streams are in separate contexts, and they have no means to actually communicate with each other. Now, obviously, one could argue, one could ask, like, why would anyone do this to themselves? So, one thing to highlight here is that interesting behavior like this in reality, and it's in general important for about scheduling as a whole, as a topic, that problems like this arise when you are getting close to the maximum utilization of the hardware. So basically, as long as you have some massively overpowered GPU and some algorithm that it can easily execute, effectively it doesn't matter how you schedule things because it will just happen to be complete in a reasonably short time frame and everyone is happy. So problem is arising when you are starting to expand in your available time slot, which is basically the reciprocal of the throughput. So that's where erroneous behavior starts to happen. That's when we started to face it too. There are options to fix it up still. So just because on the GPU level we couldn't synchronize, in general we could synchronize on the CPU level instead by using inter-process communication. But that would effectively tie our hands that the GPU execution pipeline needs to be broken several times in order to have a round trip with CPU communication. So that is something that would have a serious negative impact on the throughput. So in general, it would be much better to switch to another model where instead of having multiple separate instances of the codec running on separate processes, instead of that having a server process of a codec that is internally having either multiple threads, but honestly it's not even necessary if the API is asynchronous. So in general, to switch to a model where there is one server modeling the serving of multiple streams and then doing some kind of synchronization internally. So this is the second step, where what we do with the lines is that, so effectively the idea is that we have the same three video streams as before, so video stream 0, 1, 2. We treat each of them as command queues within OpenCL, which means that it creates, because it's in order queue, so there becomes an implicit dependency between the nodes. That's what the gray arrows mean, and we can create additional explicit dependencies between the different command queues, so that some kind of ordering is defined. So this is basically textbook example of doing a normal pipeline, so to say. One idea that may come up immediately when you look at this is that the dependency between the compute nodes is actually too harsh. So those gaps between inputs and compute could be eradicated if there was a finer granularity of compute, which in reality there is, because there are multiple kernel launches in practically every problem. But I'll come to this later. So to have the next step of efficiency, it's best if we, instead of the abstract model of OpenCL, we switch to a mind map of the hardware, like how things are actually getting executed. So what do we have? So in modern GPUs, there are all kinds of built-in schedulers. They are very good. The only tiny little problem with them from this perspective is that these are throughput optimized schedulers, so their only expectation is that I get a lot of batch kind of jobs, and I order things in a fashion that altogether everything completes the fastest way possible, but I have no concern whatsoever if there is any kind of fairness whilst I'm doing that. Now, in general, the parts in play here is that there will be two DMA engines in pretty much every discrete card that are controlling the transfers over PCI Express. PCI Express themselves is capable of having bidirectional communication at the same time. So effectively, we can assign one command queue to be input focused, one command queue to be output focused, and create a number of additional command queues that would mean to represent the actual hardware queues that exist on the device, which is I would love to say that it's an arbitrary number, but in practice it's like 2, 8, or 16. So these are the numbers that we can play with. Obviously, on this route, we start to get closer to the idea of implementing something like how we would do this with CPUs, like core affinity and things like that. But we'll come to that back a bit later. Okay, what can we do if we do this? So most trivial example is that, for example, now what's changing is that although it's exactly the same diagram, but this time, unfortunately, the arrows mean something different. So this time, it is the command queues are per hardware queue. So the blue ones are corresponding to one command queue, as well as the red ones are corresponding to one command queue. And we are using two different kinds of green to denote the first and the second compute queues. So that is also what would enable us to effectively, in a round-robin style, use alternative hardware command queues so that the second compute operation can start earlier. So with this model, actually, most times it's possible to achieve reasonably high throughput. Again, keeping in mind that in reality, the compute is never one monolithic batch, but it's a series of kernel launches. Now, what more could be done to simulate the ideal behavior of multi-core CPUs and thread affinity? Not much. Why? Because hardware queue sounds like something rigid, but in reality, for every hardware queue on modern GPUs, all the actual compute cores are virtualized resources. So it doesn't mean that we have like two queues and it's like one half of the GPU or the other half of the GPU. So independent forward progress by this alone cannot be guaranteed by any means. So what can be done instead? So every normal people in this industry would look at kernel fusion as an optimization method. So now here we do the exact opposite. This is the precise name would be kernel launch fission. So that basically instead of having one big launch one big kernel launch, which is risking that one stream is launching so much work to the GPU that it can overtake the entire GPU and keep it like that for a while. It is possible to slice up the in queues into smaller ND ranges, making it physically impossible to overtake the entire GPU and achieve some sense of control over how things can be executed. So this is what I try to capture here, is that imagine this diagram as a form of Tetris, things falling down from the top to the bottom. So the green ones are separate ND ranges on separate command queues, so like 3 command queues from 3 different streams. That's what the color coding means, but separated from one another to certain burst sizes. Then this is executed to something that can be modeled like this, that basically all modern GPUs look in a fashion that they have an array of SIMD units, and behind that with a certain length, so 32 for NVIDIA, 64 for AMD in general. And so let's call those units as like wavefronts. And there are, behind the actual physical ALUs, there are a number of virtual wavefronts ready to be executed. Reason being is that is the major latency hiding mechanisms of GPUs, that you have always multiple tasks at hand, and whilst you are waiting for some input from the memory, which is a relatively high latency thing on GPUs, you can always switch to another piece of work, a wave in this case, to work from. So now what you can do here is that effectively, and this is why I highlighted that this is experimental, so in the end even we don't use this, but it was interesting to play with. So for one particular GPU, so I'm not talking about vendors or anything, seriously one GPU and a set of kernels, it is possible to figure out some kind of trade-off between the sizes of the launches, because keep in mind as well that larger ND ranges are beneficial in order to amortize the cost of the kernel launches from host code point of view. So what we do here is just finding some kind of trade-off that doesn't hurt the throughput too much, but on the other hand tries to ensure a certain kind of independent forward progress guarantee, which in this case, for example, would mean that none of the bursts are containing enough from any of the particular command queues alone to overtake the entire GPU. So basically every one of them will make some progress by every step. Another one, which is also experimental, but this one is for application reasons, which is very important actually, that in reality there are the gaps between those steps that I highlighted. So the input, compute, output operations can be quite considerable because of driver overhead and the time to compile the kernel launches into execution buffers and things like that. So one very important thing, both from latency, because these are not just considerable overheads, but also highly non-deterministic, because drivers, how surprising, are also not written with the QoS in mind. So both from latency and throughput point of view, it is highly beneficial if it's possible to preempt the execution of work and basically try to operate quite a few frames in advance. The only major problem is that if anything is still input dependent, then we have to keep some trigger mechanism to say that to tell the GPU that okay, now you go and execute please what I already told you to. User events are possible for this, but in reality, GPUs unfortunately are not that intelligent to keep things in a hardware queue and wait for a signal. So once you fall back to this, it effectively means falling back to CPU-based synchronization, which is inefficient. Okay, where does this leave us in the end? So it's not that we were sad about it, but it wasn't a target at all, but yet we managed to achieve considerable throughput increase with the use of the techniques I described. So it's never worse than otherwise, which is, we would have been happy to make some compromise in terms of throughput, but we didn't need to. And usually it's better, but where the major difference was coming from is the up to 80% reduction in operating latency, which is actually an enabler in this kind of product. So last word is that we are expanding and looking for people who are eager to jump on challenges like this, but if you are more on the research background, then we have roles for that too. Please, once the presentation is uploaded, visit our career portal or write to our HR colleague or my other colleague, Sterios. Thank you very much. Do you have any particular questions?
Okay, thank you. So, questions? Since Mate, you are. Yep.
Sorry, one question. So, how many streams, video streams, you want to compress in the end at the same time?
In the product, in the end, we do 8 at the moment, but it's also like 2 years old GPU, so moving forward, practically anything is possible, so I can very much expect cloud-based scenarios with an arbitrary number of streams. The other thing is that this server-like solution is also used for imaging. And the imaging is a somewhat different scenario, but from programming point of view, it's like batches of images where every image is different resolution and each of them are considered as a separate stream. So that one is like the throughput version of this low latency mode.
And one more question. Does it make sense to break up the kernel fission part, which you said that one kernel launch might fill up the entire GPU, but does it make sense to break up the kernel launch into multiple launches when essentially you can only display the image once all of the launches of a given task are complete? So does it make sense to be ready with half of the work sooner, but the frame is still not ready for display? So does that part really decrease latency?
As you could see on the first diagram, in general, so basically you are interested in maximum latency, you are interested in minimum latency, and you're interested in average latency too. So basically, I think what it ups, so the standard deviation of the latency, what is really increasing if you don't guarantee independent forward progress of the streams.
Okay. Any further notes or?
Thank you. I have a short question. Just you talk a lot about kernel launch latency, and you presented many schemes of kind of reducing or hiding kernel launch latency in some places. Did you learn that NVIDIA in CUDA 10 introduced something they called, I think, NVGraph? Not a graph library, but actually for like handling like a dependency graph of operations on a GPU. And they claim that it should reduce launch latency compared to just having stuff in a stream, basically. So did you look into this?
I'll be honest, I barely heard the question, but I'm happy to answer in the break too. And also, specifically for this one, we are targeting OpenCL exclusively and non-NVIDIA hardware.
Okay.
So, yeah.
This doesn't help
No,
you.
actually, even for AMD, honestly, on paper, the hardware scheduler does support quality of service, but funnily enough, there is absolutely no way to programmatically force it to do so. Probably with HSA programming or something like that, but not with OpenCL. So, yeah, vendor-specific solutions can be tricky in this regard.
Okay, yeah, we have the least common denominator with OpenCL then, basically. Problem. Thank you.
Thank you.
Okay. Anything else for Balázs? No. Okay. So then you are free to go. Thanks again. Okay.
Kijelző.